All right, so a brief review of multiplying polynomials, and you might be wondering, why am I looking at numbers? Don't polynomials have variables with powers? Yes, but just as a quick recap of what we're doing and why, basically everything we do with polynomials, we do with numbers. And if it doesn't work for numbers, don't do it with polynomials, because we're not creating new laws of math or new patterns in math to work with polynomials. We're just using the same old ones that have always worked with numbers. So in this case up here, with the 5, 7, and 6, we know that's just 5 times, if we were to do the parentheses first, go 7 plus 6, 5 times 13, which is 65. But we also know that's equal to 5 times 7 plus 5 times 6 using the distributive property. So that's 35 plus 30, which is also 65. So basically just showing you that the distribution of the 5 to the 7 and the 6 is exactly, will get you the exact same answers you'd expect if you were to just add the 7 and the 6 and multiply by 5. Similarly down here, using that, what something some people call FOIL, I've heard it called, kind of like a double distribution. It's really kind of derived from the same idea of distribution, where you go 2 times 4, 2 times negative 1, and then 3 times 4 and 3 times negative 1. Well, this number right here on the left, this is 5. And this is 3. So our overall answer should come out to 15, because we know 5 times 3 is 15, right? So let's do this. Let's go 2 times 4 is 8. 2 times negative 1 is negative 2. 3 times 4 is positive 12. And 3 times negative 1 is negative 3. Working this left to right now, we should get 15. So we've got 6 here. 8 minus 2 is 6. Plus 12 minus 3. So this part right here gets me 18, and 18 minus 3 is 15. So it works every time. And now I'm going to do a few examples of actual polynomials, but just remember, we're not doing anything different. And if you get confused on the process, like on a test or something, work out what you think is the right way with numbers, and that's a good way to test it. So in this situation, we're supposed to multiply these things together. We've got this 6n squared, and we've got all this stuff in the parentheses. So the only thing I can do is distribution, right? That's really the only way to multiply this, because I can't combine like terms in the parentheses. So 6n squared times 5n squared, and then so we're going to do that multiplication problem, and then that's going to be plus 6n squared times negative 7n, and then plus 6n squared times 1. So I've distributed that to all the terms inside the parentheses. Now just to do the math. So the 6 and the 5, when I multiply those together, we multiply the coefficients. Of course, we get 30. And then n squared times n squared is, of course, n to the 4th. And if you're wondering, why is that? Why do they add the exponents? I'll go over that in just a second. And then the 6n squared times negative 7n. That's going to give me a negative 42 on the coefficient because of the negative 6 and negative 7. N to the 3rd for the n's. And then just plus 6n squared, because it's times 1. And so this is actually my final answer. But let's talk really quick about how I got my n's. So why was n squared times n squared n to the 4th? That's the question. Well, n squared times n squared, if I write it out like this, and you think of what n squared is, that's just n times n, and then that's being multiplied by n times n again. So you have a total of 4 n's being multiplied together, so of course that's n to the 4th. So we're using that property, that idea, that concept, to extrapolate the idea that when we multiply powers, that's what these are, powers, that have the exact same base, or the big number, we can just simply add the exponents, because it works out every time. It's just another pattern in the math. All right, let's do 2 more examples. So in this one, we've got a binomial times a binomial. So obviously we're going to do that, the thing we talked about with a FOIL, or the double distribution, however you want to think about it. And we'll just get started. So some of you guys, when you did this, I noticed you were getting your exponents mixed up. So x times 5x is 5x squared, because there's a double x's. And then we've got to go plus 7xy. And the reason I got the 7xy is because it was x times the 7y. So I've got 7 now times the x times the y. And I can't combine the x's and the y's together, so they stay separated out. And then 6y times 5x. So again, I'm thinking 6 times 5 gets me the integer of 30, or the coefficient of 30. And again, I have an x and a y. And then I go, okay, 6y times 7y. So that is going to be 42y squared. So I've got this thing now, right? And I just need to look for, can I combine like terms? And surely the middle terms, sure enough, are like terms. So let's simplify, and then that's it. So 37xy plus 42y squared. And that's really all there is to it. So it was first, outside, inside, last. And that's kind of the pattern that we see. And it's not something that I've memorized. I just think, okay, I'm going to take the x, I'm just going to distribute the x, and then I'm going to take this term here, I'm going to distribute that term. And it works out. So this one's a little bit different because it's a trinomial. We've got this, this 3-term thing here, and then we've got this binomial, this 2-term thing here, and we're going to multiply them together. And in this particular case, the binomials to the right, it doesn't really matter. A lot of times you'll see the binomial to the left of the trinomial, but it definitely doesn't really affect what we're doing. I like to work these left to right, but you could work it right to left. It really doesn't matter. It's your own preference. So I'm going to distribute this term. Okay, so I'm going to go x squared times x squared times negative 2y. Then I'm going to move on to the middle term here, 2xy, multiply that by both. Then I'm going to take the y squared and multiply that by both. So we're going to basically just distribute each and every term to the other set of terms. So we've got, let's see, x cubed, because x squared and x makes x cubed. We've got, so let's see, I did that one. Now we'll do this one, negative 2x squared y. Okay, so that term's done. So now I need to move on to my 2xy term. So I'll multiply this by x plus 2x squared now y, because the x's, we can put that into an x squared since there's 2 of them. And then negative 4xy squared, because right here there's a y in the 2xy, and in the negative 2y there's also y, so that combines. Now I want to move down because I'm going to run out of room. So then we'll go y squared times x, or xy squared. I like to try and remain somewhat consistent and put my x's first or my y's first, whatever, and then just keep that consistent throughout. And then y squared times a negative 2y, so that's 2y cubed. Now I got to simplify this thing, so I'm going to look for common or like terms, excuse me. So I've got some like terms right here. I've got, it looks to be about, oh no, there's one right here. The negative 4xy squared and xy squared, this is just 1xy squared, so those combined will get us negative 3xy squared. So when I go to combine these, I'm just going to rewrite the whole thing, crossing out what I've taken care of. So I've got an x cubed. And then what's interesting is this coefficient of negative 2 and this coefficient of positive 2, they're going to cross these terms out. So those terms are going to go away. We're not going to write anything down for those. But then I've got negative 4xy squared and positive 1xy squared, making it negative 3xy squared. And then I've got this little term here left. So this is an interesting problem because, you had some terms cancel out, and this is all you're left with here in our final answer. This is as simplified as it can get, I think. And so the trick with multiplying these is to remain organized in your process and to create maybe your own system. Do you want to list your x's first, your y's first? Whatever you decide on all those little details, just remain consistent. And I think you'll be less prone to error. All right, good luck.